very easy concept, and you get all the questions on your next quiz from this part. Okay, so it's going to be 8.1 first, and 8.1 we are going to talk about sequences. Okay, so what's going to be sequences? You see, a sequence is a function. It's a special function. It's a function that's defined on natural numbers only. The natural numbers, remember, the counting numbers. 1, 2, 3, 4, 5, 6, dot, dot, dot. Okay, so and the domain of all the sequences are going to be the same, just the natural numbers. Okay, so the definition, a sequence is just a function. Is, okay, a sequence is a function. Okay, it's a function we denote by a. This function is defined from the set of the natural number into the real number. Okay, a real number. So the definition is going to be, get the a, the function a, b, c. It's going to be defined for, okay, you get the a, well, this is it. You get the n, that take the n into the a of n. Okay, a of n. It's like x and f of x, but we don't use the x, we just use the n for the counting numbers. Okay, so it's going to be the case where n is equal to the 1, 2, 3, etc. Okay, that's going to be this notation. Since the domain of all sequences are the same, the domains are going to be just this one. So we denote a sequence by its points, its range. Okay, so since the domain, okay, of every sequence is natural numbers, is n, the set of natural numbers, okay, since the domain are going to be the same, a sequence is going to be denoted by its values, okay, or its range, Okay, so the range of the sequence is going to be, you see, a at 1, a at 2, just keep going, a at n, etc. Okay, this is one way to do it. Then again, we make it easier. So we write, okay, a at n, like f of 1, f of 2, f of 3. We write this one as a sub n. Okay, a sub n, but this n is going to be 1, 2, 3, etc. Okay, so it's a function, but since it's a special function, we use a special notation for it. Okay, so we write a at n equal to the an. Then this an is going to be, is called the nth term, because we counted, you see, 1, 2, 3, 4, 5, 6, nth term, or the general term, if you like, the general term of the sequence, Okay, so you just give us a formula for the an, then we generalize the terms of our sequence. Okay, so let's see the examples. So the first example is going to be, they usually ask you to list some member of the sequence. Okay, you may be asked, if we give you one question, we may ask you to find or list, okay, find the first, let's say, four terms of the, okay, of the given sequence. Okay, so for this sequence, the general term would be given to you. For example, you may be given a sequence with this general term, 1 over n. It's like a function, okay? We say f of x equal to 1 over x. But since for the sequence, we're just using the counting numbers, 1, 2, 3, 4, 5, 6, we write it down in this format. They ask for the first 4 terms. So this means they are interested in A1, A2, A3, and A4. You substitute and you get these numbers, okay? It's your first job, just to get to know them. Okay, that's it. So if you want to find the A1, it's going to be 1 over 1, which is 1. So that's going to be your A1, the first term. If you want to find the A2, you replace the n by 2, so that gives you 1/2. So it's going to be A2. Then you find the A3, you see A3 would be 1/3. And you find the A4, which is going to be 1/4. So these are going to be the first 4 terms of the sequence. Okay, so you have the 1, the second one is going to be half, okay, and you get a 1/3, and we get 1/4. So these are going to be our, you don't have to rewrite, I just explain it, are the first 4 terms, the first, okay, 4 terms. So we just substitute, depends on the, okay, on the given formula, the general form. Okay, any question? So the next one is going to be very popular sequence. So you may have this one, a sub n is equal to the -1, everything to the n. Okay, so this is going to be another one. So you identify the first 4 terms. So the solution is going to be, okay, the solution, if you want to find the first term, is going to be A1. You just substitute, it's going to be -1 to the 1, which is a -1. So that's the first term. If you want to find the A2, you replace the n by 2, it's going to be -1 squared, which is a +1. If you want to find the A3, it's going to be -1 to the 3rd, which is a -1. If you want to find the A4, it's going to be -1 to the 4th, which is a +1. So the term of this sequence are going to be, okay, 1, -1, 1, 1, -1. So it's like a function whose, okay, it's like a function whose range going to be containing 2 points only, -1 and +1. Okay, 1, -1, 1, -1. Any question? So don't be surprised to get this type. And sometimes you may be given a general formula, okay, for your sequence. Okay, so that's going to be the third one. The third one is going to be of this type. A sub n is equal to the 5n minus 3. See, that's a general term. It's like a function. So again, you are going to substitute to get those terms one by one. So this is going to be the solution. So we go with the A1, replace the n by 1. So that gives a 5 minus 3, which is going to be equal to 2. So that's going to be your A1. Okay, then you want to find the A2. A2, you replace the n by 2. So that gives you 5 times 2 minus 3. 5 times 2 would be 10. 10 minus 3 would be 7. Okay, then you want to find the A3. You replace the n by 3. So that gives you 5 times 3 minus 3. That would be 15 minus 3, which is 12. Okay, and finally, if you want to find the A4, so replace the n by 4. So that gives you 5 times 4 minus 3. 20, that gives you 17. So the first 4 terms of the sequence are going to be, in this format. Any question? So it's going to be used, for counting problem in computer science quite a lot, in calculus, and we are going to give you a couple of application of the sequence and you will see it. Okay, now, in order to introduce more sequences, in the application, we use a special notation that we call it factorial notations, okay? That will help us to bring more sequences. So we just remind you the factorial notation. You may have heard about it, but this is officially, you must know it, so we may be given some problems related to this one. So what is going to be, okay, factorial. What is going to be factorial notation? Okay, factorial notation. You see, this is how we're going to define the factorial notation. If n is, okay, is going to be a positive integer, is a positive integer, like 1, 2, 3, 4, 5, 6, and then n factorial, n factorial is going to be, is denoted by, this is the notation, n factorial. Okay, this is going to be n factorial, and it's defined to be a product of any number, all the numbers up to the n. Okay, so n is defined by, is going to be defined by, this is it, n factorial is going to be equal to the 1 times 2 times 3, okay, up to the n minus 1 times n. So n factorial is the product of all the numbers up to the n. Up to the n, and it's going to be useful to have 0 factorial. So we define the 0 factorial to be equal to 1. Why? Because it's going to be useful. Okay, so this is the notion of the n factorial. So you should be able to work with this one, okay? And there are different formulas that would be involved, the factorial notation. So you may be asked to, or you may have to find some of these terms. So let's check some of them. Note that, for example, 1 factorial would be just 1. So product all the numbers up to 1, we get only 1. Okay, that's going to be 1 factorial. Then if you want to check 2 factorial, you see the 2 factorial would be just 1 times 2, which is 2. Okay, if you want to find the 3 factorial, is 1 times 2 times 3, which is 6. Okay, that gives you 6. If you want to find the 4 factorial, is 1 times 2 times 3 times 4. You see over here, it's a 6 already. It's a 6. 6 times 4 is 24. Okay, if you want to find the 5 factorial, it's like 4 factorial times 5. You see it's a 1, 2, 3, 4 times 5. So it's got 24 times 5, 24 times 5, which is going to be 120. Okay, so that gives you something to remember to get these factorials. You can stop whatever you like, you see. For example, if you want to check n factorial, you can go up to the n minus 1. You see n minus 1 factorial, then times n. That's brief and easy to handle, if you like, to get these numbers. Any question? So now you may be given a sequence involving factorial, which is very popular, and they ask you to find the first 4 terms. Okay, so you may ask to write this one for us. Okay, example. So we may ask you to find the first 4 terms. Find the first 4 terms of this sequence, of the sequence AN. Okay, it is going to be a sequence AN that is given by, let's say 72 over n factorial. Okay, this is the way you may be questioned regarding the factorials. So just go ahead, get these numbers. If we replace the n by 1, a1 is equal to the 72 over 1 factorial. But 1 factorial is 1. So that gives us 72 over 1, which is a 72. So that's the first term of your sequence. Okay, so the other one is A2. A2 is 72 over 2 factorial. But the 2 factorial is just 2. So that gives you 36. So that's going to be, the second term. Okay, if you want to find the A3. Okay, A3, that gives you 72 over 3 factorials. Remember, 3 factorials is 3 times 2, which is 6. It's a 1, 2, 3. 1, 2, 3, that gives 6. So it's going to be 72 over 6, okay, which is equal to 12. And if you want to find the A4 is going to be 72 over 4 factorial. And you know that 4 factorial is going to be what? 2 times 3. Okay, 1, 2, 3, 4. So that gives you 24. So it's going to be 72 over 24, which is equal to 3. Okay, so we are not going to ask you directly a question about the factorial, but you got to be careful. You may have to use it to get these, to get these numbers for the factorial notation. Okay, any question? So this is one type of sequence, if you like. So for this type of sequence, the general term, the general formula is directly given to you. But when we do application problems, especially in computer science, you see the sequences are going to be used when you repeat something over and over and over. So you're going to create something like a machine that the machine would handle it, okay? If you handle the 3, then you get the 4, the 5, the 6, etc. So sometimes you may not have a general formula, but you may have a relationship between these terms, okay? Sometimes the term of the sequence, you see, one term can be expressed as a twice of the previous one, a sum of the 2 previous one. So there is going to be a connection between the term of the sequence. In this case, we may be able, okay, to find the general term, or we may not. So if a sequence, if the general term of a sequence is defined in terms of the sum of these previous terms, we say this sequence is recursively defined, or recurrent sequence, if you like. Okay, this means if you want to find the A5th, for example, you have to go back to the A4th. If you want to find the A4th, you may have to go back to the A3rd, okay, the third one. So these type of sequences historically are very popular. So this is, we are just getting to know the sequences, okay, various types for so far, okay. So the other one is this expression, you have to know it. The expression is recursive, something that you repeat it over and over. Okay, so this is going to be, we call it recursively defined, or in your book they call it recursive formulas. Okay, formula, or recursively defined sequence, you see, or this is it, recursively defined sequences. It's like when you want to, to build a building, if you like. So what you do, you start with the first floor. When you're done with the first floor, you go to the second floor. Based on the second, you go to the third, after the third to fourth. After a while, you know what to do. So if you go to the okay, 100 plate floor, if you like, then you go to the next one. So this is a type of sequence that we're going to talk about it. Very, very popular one. So what is going to be the definition? So this is it. So a sequence a sequence can be defined recursively. Okay, can be defined by a repeating or a recursive formula. So this means in this case you see the first term or just a few terms. Okay, that's it. So the first term, or just the first few, or the second, the first two, the first three, is going to be the first or just a couple. Okay, the first term or the first few. Okay, term of the sequence is given. Okay, of the sequence is given. Then when we get to the other one, and the end term. Okay, the end term of the sequence. And the end term is specified by a formula. Okay, it's going to be specified by a formula. Or equation. Okay, a formula or equation involving the previous terms that involves one or more of the previous terms of the previous terms. Okay, so the first term would be given. You get to the second part, the second one would be something of the first. Okay, the third term or the end term is going to be, there's going to be a relationship it can be written down in terms of the previous terms. If this is going to be the case, we say, oh, this sequence is defined recursively defined sequences. They are very popular in computer science. I also teach discrete mathematics. If you are going to be majoring computer science, you have that course instead of calculus. So it's all dealing with this type of ideas. Okay, now, and what is going to be your job? And we are going to give you one of these formulas, recursively defined, and then we ask you to list, the first 5 or 4 terms of the sequence, okay? So this is going to be the example. So the example is going to be, we would like you to write, okay, would like you to write down the first, the first, let's say 5 terms. The first 5 terms of the following recursively defined sequence. Following, okay, recursively defined sequences. So that's going to be no other problem that you have to consider. And there are 2 types. The one that you may get, defined an in terms of only one of its previous terms, or you may get more than one. Okay, so we go with the first one. This is it. The first term is given to you. A1 is equal to 1. And then you have a formula for the others. You'll be told that the an is equal to the 4an minus 1. Okay, and this is, of course, when n is equal to the 2, 3, etc. Okay, so the first term is given. So this means each term is 4 times the previous one. Okay, an equal to the 4 times an minus 1. Okay. So this is how we're going to list the members for us, solution. So you start with the first one. You say A1 is equal to 1. That's the first one. Now, if you want to find the A2, you go to this formula. You see, replace the n by 2. Replace by n by 2, take your A2 equal to the 4 times an minus 1, means 2 minus 1, which is going to be 4a1. Okay, so a2 is 4 times the previous term, a1, but the a1 is 1. So your subset is going to be 4 times 1, which is equal to 4. So a2 is equal to 4. Any question? And so then you go to the a3. You go back to the formula. This formula will generate, okay, or generate all the other terms. So you want to find the a3. You go to the formula. A3 would be 4 times the previous one. This is going to be 4a2. But a2 is equal to 4. So it's going to be 4 times 4, which is equal to the 16. So a3 is equal to the 16. Okay, and then we continue. We want to find the a4. Okay, the a4 is 4 times the previous term. It's going to be 4 times a3. So we're going to be 4 times 16, which is the 64. So the a4 is equal to the 64. You see, that gives us a general idea, really, to be able to find the big formula, but we don't want it at this level. So the a5th is 4 times the Okay, 4 times A4. So it's going to be 4 times 64. Okay, 4 times 64 would be 256. 256. This is going to be the result. Okay, and then when we go on, then we may be able to find the formula for it. So look at this one. A2 is 4 to the first. A3, 16 is 4 squared. A4 is 4 to the third, you see, and A5 is going to be 4 to the fourth. So in general, later, not now, you'll be able to guess what is going to be the AN. You see, in this case, the AN would be 4 to the N minus 1. And this is going to be your job next time. Okay, we write a couple of them, then we guess what is going to be the general formula. Okay, but guessing is not just it's good, but you have to prove your guess. You can't prove it in this course. We need that course that I talk about it. But let's get to know this first, and then we come back to this one again. Any question? So that give you the terms of your sequence. Going to be 1, you see, 1, 4, 16, 64, 256. Then you can guess what is going to be the next part. So that's a type 1. The type 1 is the fact that the general term, you see AN, is defined in terms of just one of them. Sometimes you may be able to, or you may define one terms in terms of the previous one. And this is the most popular one. This most popular one is called the Fibonacci sequence. You have to know this one by name. Okay, that's it. And that is going to be Fibonacci sequence. Okay, he's a famous Italian mathematician who just created this sequence, and today it's used all over the places. Okay, Fibonacci sequence. Now, what's going to be Fibonacci sequence? You see, this sequence is defined by the first term. The sequence is okay. This is it. The first term is equal to the 1. And in some books, they start with the f of 0. I go start with the 1. F of 1 is equal to the 1, and f of 2 is equal to 1. Okay. Then in general, if you want to find the Fn, it's going to be the sum of 2 of its previous terms. You see, so the Fn is going to be equal to the Fn minus 1, okay, plus Fn minus 2. Okay, of course, n is going to be, you have the 1 and the 2, so this n start with the 3, 4, etc. Okay, this sequence is called the Fibonacci sequence. Okay, if you find the first 5 terms that we talk about it. Okay, so let's see what is going to be the terms. So the solution, if you like. So we already got the first term is equal to 1. We have the second term equal to the 1. So we want to find the F3. You see, for F3, you go down once. This is F3, 1 down, that give F2. And 1 down again is going to be F1. Okay, so F3 is the sum of the 2 previous one, which is going to be the second one and the first one. Now we have the F2 and the F1. This is 2, 1, 1 now. So 1 plus 1 would be 2. So the third term of a Fibonacci sequence is equal to 2. Any question? That's F3. Let's find what is going to be F4. If you want to find the F4, you have to go down once, F3, once more, F2. the sum of the two previous one. So what is going to be F3? You see F3 is 2 and the F2 is 1. So that gives you 3. So F4 is equal to 3. So how about if you want to find F5th? 1 down would be F4. Once more, that gives you F3. Now, if you substitute F4 is equal to 3, and that's a 2, which is equal to the 5. So the fifth term of the Fibonacci one would be 5. So if you list them together, any question? So the first two terms are going to be given to be 1, 1. The F3 is going to be F2 and F1. 1 and 1 would be 2. So that's F3, F4, the previous one. We have the 2 and the 3, so 2 and 1, 3. The F4, that's F4, F5, the previous one, 3 and 2 would be 5. So the Fibonacci sequence, are you done with this one? So the term of your sequence are going to be of this format. If you put them together, okay, so this is going to be the case. You have the 1 and the 1, you add them together, that give you 2. You add these two together, that give you 3. These two together, that give you 5. If you want to get the 8, 13, 21, you can go on forever. So these are going to be called sequence, they call the Fibonacci, okay, Fibonacci numbers or sequence. Numbers or sequence. Okay, and these are, quite a lot of application of these numbers, Fibonacci numbers. Is used in one part of the computer science, code theory. Okay, if you want to send a message, you know that you can use the cryptography if you like. You can change it into the special code. So for those coding, Fibonacci number are going to be used, okay, to send a message and just get it back. So there are many other popular, application. It's no good for calculus because these numbers are not going to getting somewhere. So in calculus, they don't like it. They say this sequence diverges and you won't get anywhere. And there are many stories about the Fibonacci numbers, and most of them are false. This sequence, if you consider any two consecutive terms, you see the ratio of the consecutive term. If you start from here, you see the 3/2 is going to be 1.5. But if you get the 5/3, okay, that should give you something like 1.66. Okay, it's going to be 5 divided by 3. So that gives you 1.66. And if you do the 8/5, is going to be almost the same number. Okay, so that gives you 1.6, and you continue forever. Okay, so in general, if you divide the two terms of the Fibonacci sequences, it's going to be almost that 1.66. It's called golden ratio. This number over here. Sorry. So that is golden ratio is connected. There are a geometric interpretation of this ratio and quite a lot. Okay, so it's like, if you have a rectangle and the ratio of the diameter to the length is going to be this number. So that rectangle, okay, that frame, if you like, we call it the Fibonacci frame. So it's all over the places. If you want to buy a monitor for your for your computer or a TV set, If it satisfies the golden ratio, it looks nice. Okay, there are many argument about that. For example, if you get a Mona Lisa painting, okay, that's satisfy this type of ideas quite a lot. You can search on internet or on YouTube. There are a number of the very nice one. And they try to justify this form. There are many applications, but not many of these arguments are true. But mathematically, they are going to be interesting. Okay, you get quite a lot about these Fibonacci numbers. Okay, if you give me any number, I can write it down as a sum of these Fibonacci numbers. And if you want to play domino, if you like, you pick those sticks on the, and you want 2%, they start taking one each. So if you try to take the numbers in the form of the Fibonacci numbers, you are always going to be the winner. So it depends, what you want to do. When the course was face-to-face, we usually ask somebody to come and talk about it. We give you extra points, but in this format, we can't do it. But so it's nice to know the Fibonacci sequence is recursively defined. The idea that we get these numbers, it can be done again in those courses, discrete mathematics, computer science, but I'm not going to talk about it. That's how we arrive at these numbers. So it's nice get to know them, and we usually give you one question related to the Fibonacci numbers. Okay, any question? And you know that there are different stories about it. What's the original one? There is one that they say it's original, and that's the story of they call it rabbit islands. So you are going to leave a pair of rabbits, okay, with different gender, alone, okay, on an island. So what they do is they are not going to give to produce any new babies, if you like, until they are 2 months old. So we start with the first pair. This is the first pair. This is after the first month, and nothing happened. So we have again that one pair. But when we get to the second month, they are going to give birth to a new pair. So you are going to have two pairs of rabbits. Then we get to the third month. Okay, one group is going to be 2 months old again. So they produce another one, we get three pairs. And it's going to be the fourth, the fifth, the sixth, etc. So these are going to be the number of the rabbits in the island after a while, if you like, which is going to be quite a lot. So some people refer to this one as a rabbit island, and there are quite a lot if you like this type of stories. So but there are some very serious application really in linear algebra. There are a nice application of this format. Okay, I also teach linear algebra, so sometimes from time to time I give some talks to different seminars. So I did go a couple of times the connection between the Fibonacci numbers even with that course. So you see those connections that you'll be surprised that you have this type. Okay, so that is going to be the case. Again, if somebody would like to bring something, talk about it, I don't mind. I can give you extra points. Something about Fibonacci numbers. Okay, search on YouTube, you get quite a lot to get these numbers. Okay, so that is one case of these recursively defined sequences. The other thing that we are going to do it a little bit later, and just if this type of sequence is given to you, as you can see, you don't have the general term. But sometimes if these are going to be nice, you may be able to guess what is going to be the general term of the sequence. We are going to give you one, but you are going to learn something else that enable you to find it quickly. But I'm going to give you one to get the idea. Okay, so this is the problem. You have it in your book, but We give a couple of more things, then you'll be able to find it quickly. But it's fun just to think about it now. Okay, so this is going to be our next example. The next example is going to be, suppose, okay, suppose a sequence. Okay, an is recursively defined. Okay, recursively defined by, okay, that is going to be the definition. The definition is that the A1 is given to you. Suppose A1 is equal to the 32. Okay, then for the rest, if you want to find the, okay, if you want to find the AN, for example, AN is equal to the 1/2 of the AN minus 1. Okay, AN minus 1, and this is, of course, when n is going to be equal to the 2, 3, etc. Okay, so we have a sequence. It's defined recursively. And so then they ask you they ask you to write, write something like the first, okay, let's say the first 5 terms of the sequence, and then, if you like, determine. Okay, then determine a formula. And the formula, okay, for the, okay, for AN, if you like, for AN. Okay, we want to find the general formula of a sequence, if you like, okay? It's not the case that always you'll be able to find it. Sometimes it's complicated, but these cases are going to be easy. Okay, so what you're going to do, you are going to write some of the terms and to see what's going on, and you may be able to connect them together to get a general formula. Okay, these type are easy types. Okay, solution, write those 5 terms. So the first term, A1, is 32. So you have this one. Okay, get A2. So go to the formula. Each term is going to be half of the previous one. So it's going to be 1/2. The previous one is A1. A1 is 32. So that give you, okay, that give you 32 over 2. Okay, 32 over 2, which is going to be, 16. That's the A2. Any question? Okay, let's find the A3. What's going to be A3? A3 is going to be 1/2. Okay, it's going to be 1/2 of the previous one, A2. And A2 is 16. So it's a 1/2 times 16. So that gives you 8. Okay, so the first one is 16, and the second one is going to be 8. Okay, let's see what's going to be the next one. So we are going to have A4 is going to be 1/2 of the A3. So only 1/2 of the 8, which is going to be 4. Okay, so we get the 16, 8, 4. You can guess what is going to be, the next one is going to be A5. Okay, A5 is going to be what? It's going to be 1/2 of the A4. So it's going to be 1/2, and we get the 4. Okay, so that gives us a 2. And then we can continue. Okay, so you have to connect them together. So the connection is going to be, we try to connect it to this original one, which is 32, because this is 16, 8, 4, 2. The next one is going to be 1. Okay, then you get a 1/2, and then you continue. So the way you can connect, there's going to be a general formula later on, but just now. So this is 30, 32. Okay, the A1 is 32, is like 32 over 1. Okay, so this is going to be 32 over 2. Okay, and this is going to be what is a 32 over 4. Okay, and this is going to be 32. Okay, 32 over 8. 2 for 8. And this is going to be 32 over 16. So that gives you an idea of what's going on, you see. This is 32 2 squared. This is 32 2 cubed. And this is going to be 32 a 2 to the 4th. If you compare them together, this is 5. You see, this is 4. This is 4. This is 3. This is 3. This is 2. So that gives you an idea of, if you want to find the AN, it's going to be 32 on the top. 32 on the top is going to be 2 to the 1 down. 2 to the n minus 1. Okay, because the bottom one, 2 to the 4, this is 5, 4, 4, 3, 3, 2. So AN would be 32 over 2 to the n minus 1. Of course, this is going to be the case that that's it, n equal to the 1, 2, 3. And you can double check it when you write it down to get these numbers. It's going to be a special sequence. We call it geometric one later. So you have a formula for it, not to worry about. But that's give you some idea of the techniques that we may use in order to get from these recursively defined to get to the original formula. Of course, as I told you, not all of them can be done in this format, but some of them are possible, like this one that you got over here. Okay, any question? So these are going to be recursively defined sequences that we are going to have. There is another one. I can give you that one too. Then I give you a break. Okay. So this next one is also historically very interesting to get this recursively defined. Okay. So let's give you another one. This is again, you got a story behind this one. They call it Hanoi's Towers. You know that Hanoi is the capital of Vietnam. So it's something to do, there is a story related to this one. You see this sequence is going to be, suppose, okay, the sequence, we call it HN for Hanoi. Okay, HN is defined by, okay, this is the situation you're going to have. You have the H1 is equal to 1, and the HN is equal to the twice of the HN minus 1, then plus 1. And N is equal to the 2, 3, etc. It's a very popular sequence again. We call it a Hanoi sequence. Okay. So what is interesting about this one, if you check the 5 terms, what's going to be the 5 terms? Okay, so the 5 first term, H1 is equal to 1. So what's going to be H2? Look at this one. Each term is twice of the previous one plus 1. So if you want to find the H2, it's going to be 2 times the previous one, H1, then plus 1. So what is this? H1 is 1. So it's going to be 2 times 1 plus 1, which is 3. So the H2 is equal to 3. Okay, H1 is 1, H2 is 3. Okay, are ready for the H3? What's going to be H3? H3 is going to be 2H2 plus 1. What's the H2? H2 is 3. So it's going to be 2 times 3 plus 1. It's going to be 6 and 1, 7. So H3 is 7. And if you want to find H4, H4 is 3H3. Sorry, 2H3. 2H3 plus 1. So that give you 2 times what's the H3? H3 is 7. 2 times 7 plus 1. That give you 15. So the numbers are 1, 3, 7, 15. Keep going. This is also easy to find. You see, 3 is 4 minus 1. This is 8 minus 1. This is 16 minus 1. If you like, to find a formula just for your information, I'm not going to ask you today. You see, this is the 1. H2 is 3. We write that as a 4 minus 1, which is 2 squared minus 1. If we get a H3, is 7. 7 is 8 minus 1, which is 2 cubed minus 1. If you want to find the H4, is 15. 15 is 16 minus 1, which is 2 to the 4th minus 1. You see? 4, 4, 3, 3, 2, 2. So in general, Hn is 2 to the n minus 1. For n equal to the 1, 2, 3, etc. So these are going to be the general idea for these type of problems. This used to be very popular problem in old days when there was no the beginning of the computer. Okay, computer programming. People try to write so what is a relation? I give you a story of this one for you. The story of Hanoi's tower. The Hanoi's tower's story is that you see we have 3 tables. This is 1, 2, 3. Okay, you have something like a peak or just a bar here. Okay, so what I have a number of the disk here. Okay, I have a disk. That's my first disk. This is just for for 3 if you like. You see, these are going to be 1, and this is 1, 2, 3. So what I would like to do, I would like to move these 3 disks from the table number 1 to the table number 2. Okay, I want to know how many movements I need, if you like, to get this disk from the 1 to the 2 to the second one. I can use the third one too. Okay, so it's a 1, 2, 3. I want to move them to the other side, but there is a condition. The condition is each time I can move only one of them, but anytime the order must be, the smaller one must be on the top. Okay, so I want to know how many moves do I need. Okay, need to to move or to transfer these 3 days from the table 1 to the table 2 if you like. Any suggestion? How are we going to do it? Everybody understand the problem? So I have 3 disks here in this order, okay, a smaller one on the top. So I would like to move them, okay, transfer them from the first table to the second one. I can use the 1, 2, 3 anytime I like, but anytime I can only take one of them, move one of the disks, and at any time the order must be, the bigger one must be, okay, down there, and the smaller one on the top. Any suggestion? Anybody can do it? Or how many moves do I need?
It would be 5.
5. No. So the 5, can you tell us? No, it's not going to be 5.
If you move the top 2 all the way to the third one and put the bottom at the second and then move the top 2 back.
That's it, yeah. So how many moves do you need? Yeah, that's good thinking. That's the way we do it. So as you notice, it's important to, okay, to move this one, to isolate the bottom one. Okay, to isolate the bottom one. So the first thing to do is you have to move the top 2 to the other side. So how many moves do you need to move the top 2 to the other side?
2.
2. Let's see if you can do it with the 2. No, you can't do it with the 2.
So you can move the little one onto 2, and then the middle one onto 3, and then the little one onto 3, and then the big one onto 2.
Let's see if you're right. Okay, so the thing is you have to isolate the bottom one. Okay, so what you can do is you have to start the little one, okay? So it doesn't matter to the 2 or the 3. So let's put the little one here. Okay, so we have the, okay, so we have the big one and the middle one. This is 1 steps. Then we put the middle one here. Okay, that's the middle one. This is the smaller one. And okay, so that gives us a 2 move. So the big one is here. What next? So what I do is I have to move this one to this side. Okay, so that is going to be the third steps. So I've already got the big one here. So I put the middle one and the smaller one. Okay, now I isolate the big one. So I put the big one to the other side. So it's going to be empty. This is in order. So I put this one here back. Okay. So whatever I did before, I do it again here. You see, in order to get to these situations, what I did is 1, 2, 3 movements. So it took me 3 movements to move the first 2 to this position, okay, to isolate. So I just take 1 movement to the over here. So I repeat the previous movement again. So I need 3 moves to move these 2 to this bigger one. So 3 going to this side, 3 coming back, 6, 1 extra, 7. Okay, so in order to do you see, this is H3. So what I did, I do the H2. Okay, I did 1 H2 and the 1 H2 and the 1 extra. So this is 2 H2 plus 1, the one that you have. So 3 to the 3, 3, 6, and 7. So we can do it with 7 movements. And that is exactly what we got over here. Okay, so the idea is, yes, the idea is moving you see, if you want to do it for the 4 disks, So you are going to transfer the top 3 first. You know it. You can move the top 3 with 7 movements from the 1 to the 2. You isolate the bottom one. So you move the bottom one with the 1 order. The 1 and 7 would be 8, and you need 7 movement to come back. So that give you 15. 7 plus 7 plus 1, 15. If you want to do the second one, it's the same thing, 15 and 15. Okay, 30 and 1 is going to be 31. So that's a quite interesting argument. And it used, people used, the students used to write a program in the early days of the computer to be able to do this. I mean, today, you do it right away. But I used to teach those courses, and we used to give them a project to do the Hanoi Tower for 5 days, 7 days, and 10 days. So that was very interesting argument. But today, there are many. Okay, this is just start with the puzzle, if you like, but there are applications when you get to those type of disciplines. Okay, and so you have various of these stories about the Fibonacci one. About the Hanoi Tower is there is a belief. Okay, they say that there is a kind of a church, if you like, in Hanoi. It's like church. So there are people in that chair. They are doing these movements. Their discs are golden. The number of the discs they are trying is 64. Okay, it's going to be 64. And they try to move 64 discs from one side to the other side, 64 golden one. And they believe that when they are done, that would be the end of the world. But now you know it. If you put the 64 over here, they have to do this type of numbers, number of moves. H of 64 is 2 to the 64 minus 1. If you have a good calculator, you can do this one, 2 to the 64 minus 1. It's going to be something like, I think it's a 500 billion something. So if they do the movements for each disk, takes them 1 second only. It's going to be quite a lot to be able to do it. So we are safe. This is not going to be end of the world. So, there's a different story, if you like, to get these numbers. It was created by a French mathematician at the time. Okay, I'll give a break. We come back. So that was introduction of these sequences. Okay, so we are going to get a special one. There are 2, arithmetic and geometric. So I go with the geometric first. If I get time, I come back to the arithmetic, because the geometric one is the one that we usually use in science. And if you want to take calculus, or even if you don't take calculus, geometric one is more popular than the arithmetic. Arithmetic is good, if you want to work in post office, etc. But the geometry one is the one that we use in science quite a lot. So we take that one. Okay, get 10 minutes. We come back and we talk about it. It's quite easy, but important argument. Okay, see you in 10 minutes. Okay. So if we continue introducing these, there are a couple of famous sequence. Okay. So I go with the 8.3 first. Okay. We do this one. If we get time, then we go to the, okay, arithmetic, the other one. But this is more important, and we get more, you know, property. We can extend it to the notion that we are going to use in calculus in future. Okay, so what is going to be a geometric sequence? Okay, so we go 8.3 first. Because the term for the arithmetic, we cannot extend it to the, okay, we can stay with the finite number of the terms. When you want to extend it to the infinite many, then you need the geometric one. So we go with the geometric sequence. Geometric, okay, geometric sequences. So what is going to be the geometric sequence? You see, suppose two numbers given, suppose, okay, A and R are going to be our given numbers. Given numbers. Then, okay, a sequence of the form. This is going to be the form. We start with the first number A, then we start multiplying by R. You see A times R squared, and then we continue. Okay, so this is going on to get A times R to the n minus 1. So it's like A times R to the 0, A times R squared to the I, R to the n minus 1. It's like you start with the first number A, then you keep multiplying by R. So if it is going to be a sequence of this form, it's going to be called, a geometric. Okay, a geometric sequence. Okay, with a geometric sequence with the common ratio R. You see common ratio R because if you divide any of these terms, you get the same number, you get the R. So R is going to be common ratio. A is the first term of the sequence, okay, and you see AN, if you like, AN is equal to the A R to the n minus 1. This is your general term for n equal to the 1, 2, 3, etc. So this is going to be the nth term, of the sequence. So it's very easy to identify. And because of this format, they are such a popular one in science. Okay, many applications. So your first job is some sequence would be given to you. You want to determine whether this sequence is going to be geometric or not. Okay, so we want you to determine if the sequence is geometric. So you have to check to see if, if the ratio of any two consecutive term is going to be the same number. You see this one? So you'll be given 2, 6, 18, 54, and 162. You have quite a lot in your book. You have to check all the given numbers to make sure that this is a geometric sequence. Okay, the ratio of each two consecutive terms must be the same. So we're going to check to see if this is going to be the case. This is the way you're going to check it. Okay, so the ratio of a 6/2 is 3. So you see 6/2, 18/6, okay, 54/18, and 162/54. So you have to check all of them to make sure that they are all equal to each other. So if you simplify it, all of them should give you, okay, 3. Okay, so we start with the 2, you multiply by 3, you see 2 times 3 is 6, 6 times 3 18, 18 times 3 is 54, 54 times 3 162. So it's a geometric sequence with a common ratio of 3. So the sequence is, okay, the sequence is going to be geometric, okay, geometric with the common ratio of r equal to 3. Okay, any question? So this is the way you are going to check to make sure that this is going to be the case. Sometimes the sequence would be given to any question. So you just check, you can quickly check, you don't have to write anything to see if it's going to be the case. You get the first 2, then you have the common ratio. See, 6 divided by 2, you get the 3. So just check it quickly. 3 times 6, 18. 18 times 6 is 54. 54 times 3 is 162. So you realize that this is going to be true. Okay, sometimes they don't list the members. They just give you a formula. Okay, so they give you this formula that an is equal to the 2 to the negative n, or n equal to the, okay, 1, 2, 3, etc. Again, you just write a couple of terms to find out this is going to be the case. So the solution is, you better rewrite it. An is like 1/2 to the n. That gives you better understanding to find it quickly. Okay, so just write a couple of terms to confirm it. So the first term is 1/2. You see the next term is 1/4. So then the other term is going to be 1/8. And you realize that this is going to be the case. Because the first term is 1/2. You multiply by 1/2, you get 1/4. You multiply by another 1/2, you get a 1/8, etc. Or if you divide the second term by the first term, you will see that common ratio. Okay, so the sequence is geometric. Okay, the sequence is geometric. Okay, geometric with the common ratio of r equal to the 1/2. Okay, so this is going to be in the case. You just list them together to get to that number. Okay, so this is going to be one version. Just want to check to show you one of them that this is not the case. Give you another one. Any question? You get quite a lot in your assignment. Just pick a couple of them when you want to give us those 5 sequence Make sure you know it. Okay, let's check this one to see when it's going to be something wrong. And this is 2, 4, 2, 4, 16. Okay, 64. Then I have 256. Okay, 256. So just quickly check. You divide these two together, you see to find what is going to be the common ratio. So the solution is going to be, you divide the 4 by 2, so the common ratio must be 2. Okay, so you know that 16 divided by 4 is not 2. Okay, you divide the 16 by 4, so that give you 4. So you're not going to continue because the common ratio are, there is no common ratio. Okay, so the sequence is not going to be, is not geometric. Okay, so this is the way you are going to, okay, you are going to reject it to get these numbers. Okay, any question? Now, what we can do next is we have a formula for the general term of the sequence. So sometimes they may ask you to, okay, to get the sum of the numbers. Okay, so you have these type of problems. Example, I give you the general formula. So they may give you a couple of terms and they ask you to find, okay, find the n term. Okay, find the n term of the geometric sequence of the given geometric, okay, geometric sequence. That is going to be the case. So what is the sequence? The sequence is 10, okay, 9, we have 18 over 10, and then we have 729 over 100, etc. Okay, so you have a couple of terms. So you want to know what is going to be now the nth term of the sequence, or sometimes they may ask for the, for the specific one. So what you are going to do is you have to know that you see solution. So the general term of the sequence, you see the nth term of the sequence, okay, an is equal to the first term, a or a1, doesn't matter. You can call it a1 if you like, the first term, r to the n minus 1. So a1 is the first term, which is equal to the 10. R is the common ratio. You have to find it. Since they tell you that it is geometric sequence, so you have to divide, two consecutive terms, the second by to the first one to get the R. It doesn't matter. So your R is equal to, you divide the 9 by 10. Okay, so that give you 0.9. 0.9 is your common ratio. Okay, any question? It doesn't matter, because it's already giving you this information that's geometric. So you can divide the 9 by 10, or you can divide 81 over 10 divided by 9. They'll give you the same number. Okay, so we go back and we write it. AN is equal to A1 is equal to the 10, okay, times 0.9, 0.9 to the n minus 1. Okay, so that gives you the general term of your sequence. N is equal to the 1, 2, 3, etc. And sometimes in your book, they ask for the 9 term, the 10 terms. Okay, so you write this general term, and then if they ask for it, then you can, you can find it if you like. Okay, so, in this problem, they just go with I go with the end. So, for example, if you've been asked, then this is the way we're going to find it. If you want to find the 9th term, A9 is going to be 10. You are done. If you ask for the general 10, you're done. But I just show you the way you may be asked to find it in your book. So it's going to be 10 times 0.9, and this is going to be 9 minus 1. So it's going to be 10 times 0.9, okay, to the 8. Then you have to use your calculator if it's going to be on the test to find it. So for example, the 9th term of this sequence is going to be 4.304, 621. If they ask, there is one in your book. So we just want to make sure that you won't be surprised, and then you'll be able, you'll be able to find it for us. Okay, so this is going to be a geometric sequence. So why these sequences, especially the geometric, are so popular? They are going to be popular because you see, if a sequence is given to you, you would be able to find, sometimes, or you would like to find the sum of the sequence, You know that this sequence can go on forever because your n is counting numbers. N is 1, 2, 3, 4, 5, 6, forever. So there is going to be a case that sometimes you stop and you would like to find just a finite sum, and sometimes you don't stop. You want to get the general term of the sequence. So in the case of the geometric one, is very, very popular, but we need a couple of notation to be able to find it. Okay, let's see if we can get that notation, and if we can get somewhere to get these formulas. Okay, any question? So get to know it. A1 r to the n minus 1 is very popular for those general formula, because you put this in and we get the numbers. So let's see what is going to be the most important part. The reason that we study this section is the following. So let's see what is going to be what is going to be the sum of terms of the sequence. Okay, so what is going to be the sum of n terms of a sequence? And then we get the geometric one, which is a very nice formula that we use in science. Okay, so this is it. If you give me a sequence, if a sequence an is given, then a1 plus a2 plus a3 up to the an, you see, is going to be the sum of n terms of the sequence of the sequence is denoted okay, is going to be denoted by Sn. S for the sum, N for the number of the terms that we are going to have. So if I ask for S1, so this means just sum of the one term. It's just A1. Okay, sum of one term. If I ask for the S2, so this means I'm interested in sum of the two terms. Okay, if I ask for the S3, so this means I'm interested in the sum of the three terms. Okay, and in general, Sn is A1 plus A2, A3 up to the n. So this is the sum of the n terms of the sequence. Any question? Now, sometimes we use the so-called the sigma notation. The sigma notation is instead of listing all the members, or Sn is equal to, we write sigma, means sum. Then we write the A sub I from 1 to n. What does it mean? This means you start from I equal to 1. If you put I equal to the 1, that gives you A1. So this means sum plus. Then you replace the I by 2. So that gives you A2. This means plus. You continue. How many times you continue? From I equal to 1 to n. Up to the n. Okay, so we call it the sigma notation, that we are going to extend it later on. But for the time being, we can get away with it, okay, to get these numbers. So the sum of the first n terms of a sequence, or just this sigma to get these numbers. Of course, if it's going to be 5, 6, 10, you can do it. But how about if I give you 100 terms? You cannot list all the hundreds. Okay, 1,000, 10,000. You cannot list all of them. So what you need is, you need to be able to find a formula for it, okay? A nice formula for this type of numbers. When it's a very special one, like the geometric one, we be able to find this type of formula for it. Okay, so that's the general. If you are going to be in sequence, that's in calculus 2, of course. It's just the beginning of some ideas that we just put it in an easy form so that we be able to understand it. Okay, so you'll be given a sequence. If you want to add the terms of the sequence, we use the Sn formula. So the Sn means add n of these terms together. So what we'd like to do is, what would happen if I give you a geometric sequence, okay? So that's the interesting part. The interesting part is going to be if, okay, if an, you know that, equal to the a1 r to the n minus 1 is a geometric sequence, geometric sequence. Then what's going to be this time? Okay, then what is going to be your Sn? You see the Sn is equal to the first term. Let me write it down. The first term, the second term, the third term, up to the last term. List it down to see what's going to be the case. Sn equal to, the first term is just the A1. That's the first term. The second term, you see A1R. The next one, a2 r squared. I just continue. Getting to the last term is these are all a11. The last one would be a1 r to the n minus 1. Okay? So if you want to find the sum of the n terms of this geometric sequence, this is the way you're going to find it. Okay, you add them together. But you can use a trick to get a nice formula for it. Let's see what's going to be the trick. So you see, what I'm going to do is, remember the r was a common ratio. I am going to multiply everything by r from this both sides. Okay? Multiply by r. Why? Because it's useful. You see, multiply by r, it's going to be r Sn equal to. Multiply each of these by r. You see, this is a1, get the r. Okay, this is going to be plus. This is a1. You multiply this one by r. You already got the r. So r times r would be r squared. Okay, the next one. It's a1. This is r squared. You multiply by another r, make it to the r cube. Just continue. Continue. What's going to be the last one? The last one is a1 r to the, okay, that's n minus 1. That gives you r to the n. I push it forward, if you like, by 1 power. Okay, so I got the Sn from the first one, and I got the, I multiply by r, I make it to the Rsn. I'm looking for Sn. So what I'm going to do is, I'm going to subtract this. Okay? If I want to subtract it, I have to change all this sign, you see? Negative, 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 negative. So over here, I have Sn minus Rsn. What is the other side? Any suggestion? What's the leftover? If you subtract it. Subtract. Did these two? Cancel out. Because this is a1r, it's a negative a1r. So these two would be out. These two, because this is negative, this is positive, would be out, would be out, would be out. Okay, so this everything would be out. What's the leftover? A1 from the first one. From the second one, see, up to the n minus 1 would be out. You get this last part here. Minus A1R. You see? It's a very nice trick. It's a very historical, result. The way they are going to know, they are going to find it. So I got the first one, Sn. I multiply everything by R, so I push the powers one forward, if you like. So everything would be canceled out. Remember, I'm looking for Sn, so I can do it now. I factor out the Sn, that give me 1 minus R. Okay, Sn. I factor out the A1, that give me 1 minus. I'm sorry, this is R to the N. R to the N. So that give me R to the N. So the Sn is going to be equal to, we get a fraction on the top A1, times 1 minus r to the n divided by 1 minus r. This is one of the most popular formula in mathematics. You see, this is what? This is the sum of the first n terms, okay, of the geometric sequence. Okay, so the sum of the sum of the first n terms of a geometric sequence. You have to memorize it or bring it to the test, we don't mind, because we're going to see a couple of problems related to this formula, and we are going to extend it later on. But for the time being, you see they give you just a couple of them and they ask you to find it. Okay, any question? I just proved it for you. You see, you don't need the proof. I just prove it for you so that you believe it and you understand it really. But you just need to memorize the last formula. We do this one in calculus too. This type of argument that I did over here. And it's such a strong tools, okay? You can do many more problems in science just using this one, okay, this formula and this argument. Sequences are going to be extended later on, but if you want to do anything for the extension, you go through this one. So that's why I just rushed this one to this section so that you make sure that you know, you get this one. So the example is, that's it, a sequence would be given. Let's get one example and we leave the rest for the next time. Okay, we do it, this is just finite, we do the infinite later on. So any question, make sure you memorize it correctly. You see A1 is outside the parentheses, the top is 1 minus r to the n, this is 1 minus r. You know that when you want to use this formula, r is the common ratio, which can be found quickly, common ratio, and the a is the first term. You need only these two numbers to be able to find it. Okay, so just quickly give you one example, and then we leave it for we finish it next time. And there are going to be some very nice application. So for the time being, this is going to be the application of this formula. Okay, example. You may be asked, find the sum. Okay, that's it. Find the following sum, if you like. Sum. This is it. You would like to find the sigma of, okay, sometimes write it in sigma form, 1/2 to the n from 1 to 10. So you have to list it to understand it. What type of sum is this one? It's a geometric sum. But I list it so that you can see it. You see, look at this one. You write it down in expanded form, we call it. So that's a sigma. You know, we give you more example in this notation of a sigma if you haven't seen it before. You see, this means the first term. You replace the n by 1, that gives you the first term, 1/2. Okay, 1/2 to the first is the first term, plus the second term is going to be 1/2 squared. Okay, 1/2 to the third, etc. So if you think about it, this 1/2 is going to be, you see, this is like a 1/2. This is a quarter, and this is the 1/8. So as you can see, this is a geometric sum. It's a geometric. First term is 1/2. The common ratio is 1/2 because it's 1/2, 1/2 times 1/2 a quarter times 1/2, or just divide the second one by the first one. Okay, so you note that it is a geometric sum with what? A, the first terms, 1/2. Common ratio, 1/2. You see, if you like, you see a quarter divided by the 1/2 would be 1/2. This is the way we find it. Okay? So the formula for the Sn, remember, Sn is A1, 1 minus r to the n over 1 minus r. But they ask for the 10 only. So you need the S10. S10 is equal to A1, the first term, 1/2, times 1 minus. Okay, I write the S10 so that you see, get the S10. S10 is equal to A1 times 1 minus r to the 10 divided by 1 minus r. So, we use your calculator to get this. So it's S10 is equal to A1 is 1/2 times 1 minus 1/2 to the 10 divided by 1 minus 1/2. 1 minus 1/2 would be 1/2, and the 1/2 and 1/2 would cancel out. So your S10 is equal to 1 minus 1/2 to the 10. You can use your calculator. So 1 minus 0.5 to the 10. So we can use your calculator to find the actual number. Okay, so that's going to be the I don't have it there for the, no, I don't have the final answer, but you can use your calculator, just leave it as is. But on the test we expect you to to apply it, get your calculator and find the numbers. Okay, so this is how we deal with this geometric sum. You must know the formula, okay, the Sn, and then you just count, you ask for the 10 members, so you just substitute to get the result. I've given this one on the test. Some people, they list all the members and they add them together. We would like you to use the formula. So you can do it for the 10, but I give you 100, then you won't be able to do it. We continue, okay, next time, give you more examples. The way we are going to be interested in, we are not interested in the 10, 100 terms. We are going to be interested when these numbers going on forever. We call it infinite sum. That's the, eventually this is what we are going to be interested in. But we talk about it on, okay, we talk about it on Monday. And so we have to give you a short quiz. I just check to see if I give you a practice quiz, then we prepare you for that quiz shortly and the final review, okay? There are a couple of more things to talk about it, but otherwise we are done. And then we start working for the final, really, that's one. Okay, any question? So I will check your test and I post it. Then let me know if you have any question. Okay, have a good night and take care. Bye-bye.
All right, thank you.
Bye-bye, thank you.
Thank you.